I was told to measure reliability, not consequences, while the orders kept coming faster than the tests. Each launch worked, and still it felt incomplete, as if something important was left unnamed. The system wanted numbers, not what the sound did to men on both sides of the rails. I wrote only what I could prove, and left the rest to echo on its own. By the summer of 1941, the Soviet Union faced a rapidly deteriorating military situation along its western frontier. On 22nd June, German forces launched Operation Barbarossa, advancing across multiple axes with speed and coordination that overwhelmed many Red Army formations. In the opening weeks, Soviet units suffered heavy losses in men, equipment, and territory. Command structures were strained, and industrial evacuation eastward had only just begun. Under these conditions, the Red Army sought any means to slow the advance and disrupt German concentrations long enough to restore defensive coherence. In the Moscow region, away from the immediate front but fully aware of its pressures, a small group of engineers continued work at artillery research facilities that had existed since the interwar period. Among them was a mid-level engineer assigned to experimental rocket artillery systems. His work was not glamorous and was largely insulated from battlefield drama. The laboratory schedule followed routine rhythms: inspection of test data, maintenance of launch frames, correspondence with production workshops, and the careful logging of incremental design changes. At the time, rocket artillery was not regarded as a decisive weapon. It was one of several experimental paths the Soviet military had explored since the early 1930s. The engineer's responsibilities were narrow in scope. He worked primarily on stabilization and ignition consistency for unguided rockets designed to be launched from truck-mounted rails. These rockets, designated M13 in their standard configuration, were fin-stabilized projectiles with solid fuel motors. Their theoretical advantages were simplicity, speed of manufacture, and the ability to deliver saturation fire over a short period. Their disadvantages were equally clear: poor accuracy compared to tube artillery, sensitivity to manufacturing tolerances, and limited range control. Before the war, such shortcomings had relegated the system to a low priority. The Red Army favored conventional artillery with established doctrines and predictable results. Rocket artillery units existed mostly on paper or in limited experimental formations. The engineer understood this context well. His daily work was defined less by ambition than by compliance with technical instructions issued by the main artillery directorate. These instructions emphasized reliability over innovation. Deviations from approved designs required justification and approval, which could take months. In late June 1941, the operational situation forced a change in emphasis. Reports from the front described dense German troop movements, motorized columns, and temporary assembly areas that were difficult to engage with conventional artillery due to mobility and air superiority. Soviet commanders requested weapons capable of rapid, concentrated fire followed by immediate displacement. Rocket artillery, with its short firing cycle and truck-mounted mobility, suddenly appeared more relevant. Under pressure from military authorities, testing schedules were accelerated. The engineer and his colleagues were instructed to prepare existing rocket launchers for field trials under combat conditions. There was no time for comprehensive redesigns. Instead, attention focused on identifying limitations that might compromise performance or safety when used by frontline units with minimal training. One persistent problem involved rocket dispersion. Test firings conducted before the war had shown wide impact patterns even under controlled conditions. Variations in propellant burn, slight misalignments in fins, and inconsistencies in rail geometry all contributed. The engineer's task was to examine whether small adjustments could improve stability without disrupting mass production. He began by reviewing earlier test logs, some dating back several years. These documents recorded not only impact patterns, but also acoustic observations noted almost as an afterthought. During certain firings, observers had remarked on a distinctive sound produced by the rockets in flight. The descriptions were inconsistent. Some compared it to tearing fabric, others to a rising mechanical howl. No formal analysis had been conducted. Sound characteristics were not considered militarily relevant. The engineer initially regarded these notes as curiosities. His focus remained on measurable factors: dispersion radius, failure rates, ignition delays. However, as new test firings were scheduled under wartime urgency, the sound phenomenon became harder to ignore. During a late June test outside Moscow, a full salvo produced a sustained, high-pitched roar that carried far beyond the test range. Personnel unfamiliar with the system reacted visibly. Some flinched, others turned instinctively toward the sound even before the rockets impacted. The engineer observed these reactions carefully. He did not interpret them emotionally, but noted their consistency. Even trained technicians paused during the launch sequence. The sound was not merely loud, it had a particular rising quality, beginning abruptly and intensifying as the rockets accelerated along the rails and into open air. It differed from the sharp report of artillery or the steady drone of aircraft. From a technical standpoint, the sound suggested aerodynamic or exhaust-related causes. The M13 rocket used angled exhaust ports to impart spin, supplementing fin stabilization. This spin improved flight stability but introduced complex airflow interactions. The engineer suspected that minor variations in port geometry or rail spacing might amplify resonant effects during launch. At the same time, production constraints limited what could be altered. Factories tasked with manufacturing rockets were already under strain, adapting to wartime conditions and evacuations. Any proposed change would need to be simple, reproducible, and justified as necessary for combat effectiveness. Improving accuracy offered a clear rationale. Altering acoustic characteristics did not. Field reports soon provided additional context. The first combat use of the rocket launchers occurred in early July 1941 near Orsha. Although official documentation was sparse, informal accounts circulated within technical circles. The rockets delivered heavy damage to German positions, but accuracy remained inconsistent. More notable, however, were comments about the psychological effect of the launch itself. German troops reportedly reacted with confusion and alarm during the initial salvos. The engineer read these reports cautiously. Wartime accounts often exaggerated effects, and second-hand information was unreliable. Still, the convergence of battlefield observations and laboratory experience suggested that the sound produced by the rockets was not incidental. It was a byproduct of design choices made for stability and ease of manufacture, yet it had observable effects on both friendly and enemy personnel. Despite this, the engineer did not propose any immediate changes. His position did not allow for speculative recommendations, and there was no directive to pursue psychological factors. Instead, he continued routine adjustments aimed at reducing dispersion. These included minor refinements to rail alignment and stricter inspection of exhaust port angles. Each adjustment was documented, tested, and reported through formal channels. During subsequent tests, he noticed that even small changes affected the acoustic profile of the launch. Slightly improved alignment produced a cleaner, more uniform sound, while greater variance led to irregular noise patterns. The relationship was not fully understood, but it was consistent enough to warrant attention. The engineer began recording sound characteristics alongside ballistic data, adding annotations to test logs that had previously ignored such details. These annotations were technical rather than interpretive. He described frequency ranges, duration, and perceived intensity without speculating on psychological impact. This approach aligned with institutional expectations. Engineers were to present data, not conclusions beyond their remit. By mid-July, pressure from the front increased. Requests arrived for additional launcher units and rockets, often accompanied by urgent timelines. The engineers' facility shifted from experimental pacing to near-continuous testing. Errors became more frequent, not due to negligence but exhaustion and limited resources. In one instance, a misaligned rail caused a rocket to shear slightly during launch, altering its trajectory. The incident prompted a review of safety margins. It also reinforced the limitations of the system. Rocket artillery offered speed and volume but demanded careful handling. Its effectiveness depended on coordination between design, production, and field use, coordination that wartime conditions undermined. The engineer understood that improvements would be incremental at best. As July drew to a close, he faced a growing awareness that the system's most distinctive feature might not be accuracy or firepower alone. The sound produced during launch was consistent, reproducible, and noticeable even to those with no technical background. It emerged naturally from design elements intended for other purposes. Whether this characteristic could be controlled or exploited remained an open question. For the moment, the engineer returned to his assigned tasks. Test schedules were posted, reports compiled, and correspondence sent. The front demanded weapons, not theories. The laboratory continued its work under the constant awareness that time and margin for error were both diminishing. By early August 1941, the Red Army's operational situation had worsened across multiple fronts. German formations continued their advance toward Leningrad, Moscow, and Kyiv, exploiting breakthroughs and encirclements. Soviet artillery units, often forced to retreat or reposition under air attack, struggled to maintain sustained fire. In this environment, rocket artillery units, still few in number, were deployed more frequently, sometimes without full integration into existing command structures. Reports from these deployments reached technical departments irregularly. Some arrived as formal after-action summaries. Others circulated as copied notes or verbal accounts passed through administrative channels. The engineer reviewed what material he could obtain, comparing it with laboratory data. Patterns began to emerge, though not always in ways anticipated by pre-war doctrine. Operationally, rocket artillery units faced recurring difficulties. Accuracy remained inconsistent, particularly at longer ranges. Crews with minimal training sometimes misjudged firing angles or failed to secure launch frames properly. In several documented cases, rockets impacted short of their intended targets or dispersed widely across uneven terrain. These shortcomings limited the weapon's suitability for precise fire missions. At the same time, accounts consistently mentioned the immediate reaction of enemy troops during launches. German units reportedly sought cover or halted movement when rocket salvos were fired, even when the impacts themselves caused limited casualties. Soviet observers noted moments of hesitation and disorder that conventional artillery did not always produce. Such observations were not framed as decisive advantages, but they were repeated across different sectors. Within the engineer's facility, this information created a quiet tension. Official design objectives still emphasized reliability and manufacturability. Psychological effects were not part of technical specifications, yet field commanders increasingly valued any factor that disrupted enemy tempo, even briefly. The disconnect between formal doctrine and battlefield reality became more pronounced. Testing continued under accelerated conditions. Launches were conducted with varying rail configurations, propellant batches, and ignition timings. Failures occurred with uncomfortable frequency. Some rockets failed to ignite properly, while others exhibited unstable flight shortly after launch. Each failure required investigation, often delaying subsequent tests and straining limited resources. The engineer focused on root causes rather than symptoms. He identified that small deviations in exhaust port angles, within accepted tolerances, could alter both spin rate and exhaust interaction with the surrounding air. These changes affected not only flight stability, but also the sound generated during launch and early flight. The relationship was complex and difficult to quantify without specialized instruments, which were unavailable. He proposed tighter tolerances for certain components, particularly exhaust port machining. The proposal was modest and framed strictly in terms of reliability. It was reviewed by supervisors and forwarded to production authorities, who responded with reservations. Factories were already operating under severe constraints. Tighter tolerances risked slowing output, which frontline units could not afford. The proposal was approved only in limited form. Select batches would receive additional inspection, but mass production standards remained unchanged. This compromise reflected broader tensions within the Soviet war economy, the need to balance quality against quantity under existential pressure. Meanwhile, rocket artillery units experienced both success and loss. In some engagements, rapid salvos allowed Soviet forces to disrupt German assembly areas before withdrawing. In others, launch positions were detected and targeted by counter-battery fire or aircraft. The distinctive sound of the rockets, while alarming to the enemy, also revealed the launcher's location almost immediately. This vulnerability concerned commanders. Rocket artillery doctrine emphasized shoot-and-scoot tactics, but execution varied. Crews sometimes lingered too long, attempting to observe results or reload. Casualties followed. These incidents prompted questions about whether the weapon's distinctive characteristics created unacceptable risks. The engineer became aware of these concerns through internal memoranda. One document noted that while the rocket system's effect on enemy morale appeared significant, its acoustic signature compromised concealment. The memo stopped short of recommending changes, instead requesting further evaluation. Such evaluation fell ambiguously between departments. Acoustic analysis was not clearly assigned to any technical group. Ballistics specialists focused on range and dispersion. Production engineers focused on output. The engineer's annotations on sound characteristics remained unofficial, attached to test logs rather than formal reports. Despite this, he continued to collect data. During tests, he positioned himself at varying distances and angles from the launcher, noting how sound propagated across open ground and forested areas. He observed that terrain influenced perception significantly. In open fields, the sound carried far but dissipated quickly. In wooded areas or urban fringes, it echoed and lingered, creating the impression of greater volume and duration. These observations aligned with field reports from different sectors. Units operating near forests or villages reported stronger reactions from both enemy and friendly troops. The engineer did not attribute this to fear alone, but considered sensory overload under combat conditions. Sudden, unfamiliar stimuli could disrupt coordination even among experienced soldiers. Still, translating such observations into actionable design changes proved difficult. Reducing sound would likely require altering exhaust configuration, potentially compromising stability. Amplifying sound deliberately was not an accepted design goal and lacked doctrinal support. Any proposal framed around morale effects risked being dismissed as speculative or inappropriate. As August progressed, the engineer witnessed increasing strain within his own facility. Personnel were reassigned, some to evacuation duties, others to new projects deemed more urgent. Test schedules were revised frequently. Equipment shortages became more acute. Yet rocket artillery remained in demand, its perceived battlefield value outweighing its limitations. One incident during a mid-August test underscored the system's fragility. A launcher experienced partial ignition failure, causing two rockets to ignite out of sequence. The resulting vibration damaged the rail assembly and forced an immediate halt. No one was injured, but the incident prompted a temporary suspension of tests. During the subsequent review, the engineer emphasized the interaction between ignition timing and exhaust dynamics. He argued that irregular ignition not only affected trajectory, but also produced erratic acoustic signatures, which could confuse crews and observers. His remarks were recorded but not prioritized. The review concluded with instructions to reinforce inspection procedures and resume testing as soon as possible. The broader questions remained unresolved. At the front, the operational tempo left little room for experimentation. Rocket artillery units were used where available, often in improvised roles. Their successes were uneven but notable enough to secure continued support from higher command. Failures were attributed to training and deployment rather than design. Within this context, the engineer found himself increasingly aware of the gap between what was measured and what mattered. Official metrics focused on dispersion, range, and reliability. Field reports suggested that disruption, momentary confusion, forced pauses, and loss of cohesion was equally significant. The sound produced during launch contributed to this disruption, whether intentionally or not. Yet acknowledging this openly required navigating institutional boundaries. The engineer did not possess authority to redefine design objectives. He could only present data and hope it was interpreted broadly. As the war intensified, the space for such interpretation narrowed. By late August, new directives arrived emphasizing rapid delivery of launchers and rockets to units defending approaches to Moscow. The engineers' facility prepared to shift from testing to direct support of production modifications already approved. Experimental work would be reduced. Before this transition, he compiled his test logs and annotations, organizing them carefully. He did not draw conclusions beyond his mandate. Instead, he ensured that observations about ignition consistency, exhaust configuration, and acoustic effects were clearly recorded and accessible. Whether these records would influence future decisions was uncertain. For now, the immediate demands of war took precedence. The engineer returned to routine tasks, aware that unresolved questions about the system's limitations and unintended effects remained. By September 1941, the German advance toward Moscow had forced the Soviet command to reassess every available means of defense. Industrial facilities in the western regions were dismantled or evacuated eastward. Research institutions that remained operational did so under compressed timelines and frequent disruption. The engineer's facility, still functioning near Moscow, now worked under directives that emphasized immediate applicability rather than long-term development. Rocket artillery occupied an ambiguous position within this framework. It was no longer experimental in the abstract, yet it had not been fully codified into established artillery doctrine. Units existed, production continued, and results were observed, but formal guidance lagged behind operational reality. This ambiguity created space for limited initiative, though always within constraints. During this period, the engineer was assigned to a short-term liaison role, supporting a Guards mortar unit newly formed to operate rocket launchers. His task was technical rather than advisory, to observe equipment performance under field conditions and report mechanical issues directly to the manufacturing authorities. Such assignments were increasingly common, reflecting the need to close gaps between design and use. The unit was positioned west of Moscow, rotating between concealed firing positions and temporary staging areas. The engineer arrived with a small group of technicians and basic instruments. Living conditions were austere. Observation was conducted under operational security with limited opportunity for extended testing. Launches occurred at irregular intervals, dictated by intelligence and command decisions rather than schedules. From the first live salvo he witnessed in the field, the difference between laboratory testing and combat use was evident. Crews worked quickly, often under stress. Alignment procedures were simplified. Calculations were approximate. The priority was speed. When the rockets launched, the familiar rising sound filled the air, louder and more pronounced than in controlled tests due to the proximity of terrain features. The engineer noted crew reactions as carefully as rocket performance. Despite training, even experienced operators showed momentary tension during launch. Communication paused until the last rocket left the rails. Only then did orders resume. This pause was brief but consistent. The engineer recorded it without interpretation. Enemy reaction was harder to observe directly, but reports from forward observers indicated immediate disruption during rocket salvos. German units altered movement patterns, sometimes dispersing prematurely. In several instances, counter-battery fire was delayed or misdirected. These effects were temporary but operationally relevant. One engagement in late September provided particularly clear observations. The unit fired a concentrated salvo against a suspected German assembly area near a forest edge. The rockets impacted unevenly, causing limited physical damage. However, subsequent reconnaissance reported that German elements abandoned the area and repositioned farther back than expected. Intercepted communications suggested confusion regarding the nature and scale of the attack. The engineer reviewed these reports alongside his own observations. The weapon's accuracy limitations remained evident, yet its capacity to impose uncertainty was increasingly difficult to dismiss. This uncertainty stemmed not only from explosive effects but from sensory impact. Sound, smoke, and sudden saturation. At this point, the engineer faced a decision that was unofficial and personal rather than doctrinal. He could continue to report purely mechanical observations, or he could frame certain data in a way that highlighted operational relevance without explicitly invoking psychological terminology. The latter carried risk. Overstepping defined technical roles could invite scrutiny or dismissal. He chose a cautious middle path. In his reports, he emphasized the relationship between ignition consistency, exhaust configuration, and launch predictability. He included detailed descriptions of how irregular ignition altered not only dispersion, but also the temporal and acoustic pattern of salvos. He noted that uniform ignition produced a more cohesive launch event, with all rockets leaving the rails in rapid succession and generating a sustained, continuous sound. He avoided stating that this sound had a psychological effect. Instead, he described its operational correlates: reduced reaction time between first and last impact, increased difficulty for observers to distinguish individual launch points, and compressed engagement windows for enemy countermeasures. These were technical observations grounded in sequence and timing. The reports were forwarded through the unit's command to higher technical authorities. Whether they would be read attentively was uncertain. Still, the engineer continued to refine his observations. During subsequent firings, he worked with crew chiefs to ensure consistent ignition procedures. This involved minor adjustments to wiring checks and sequencing rather than hardware changes. These adjustments were within existing guidelines and required no formal approval. The result was a noticeable reduction in launch irregularities. With more consistent launches, the acoustic profile became more uniform. The sound did not change in character, but its continuity increased. The engineer noted that this uniformity correlated with smoother crew operation and faster displacement after firing. Crews appeared more confident when launches proceeded as expected, without unexpected delays or misfires. This correlation reinforced the engineer's belief that technical reliability and sensory effects were intertwined. A weapon that behaved predictably reduced strain on operators and compressed the time exposed to enemy response. These benefits were measurable, even if their causes were not fully articulated. The risk in pursuing this line of thinking lay in its informality. No directive authorized optimization of acoustic characteristics. Any perceived deviation from established goals could be interpreted as unnecessary experimentation. The engineer therefore framed all recommendations strictly in terms of reliability, safety, and operational timing. As October approached, conditions worsened. Weather deteriorated, affecting both rocket performance and crew endurance. Moisture influenced propellant behavior, increasing the risk of ignition delays. The engineer documented these effects meticulously, aware that winter conditions would magnify them. In one instance, a delayed ignition caused a staggered launch sequence that disrupted the intended salvo pattern. The sound became uneven, with gaps that broke the sustained effect. Enemy response in this case was faster and more precise, resulting in near-miss counter-battery fire. No casualties occurred, but the contrast with previous engagements was notable. This incident strengthened the engineer's resolve to emphasize ignition consistency. He requested additional time with the unit to refine procedures before the onset of winter. The request was granted informally by the unit commander, who valued practical improvements regardless of their theoretical framing. The engineer's actions remained within acceptable boundaries. He did not alter hardware specifications or issue unauthorized instructions. He worked through existing hierarchies, adapting procedures incrementally. The risk he assumed was reputational rather than legal, that his focus might be seen as misplaced if results did not justify attention. By mid-October, his liaison assignment concluded. He returned to the research facility with field notes, test logs, and reports endorsed by the unit commander. The situation around Moscow had stabilized temporarily, but the threat remained acute. Rocket artillery units were now considered an established component of defensive operations, though still not fully standardized. The engineer submitted his compiled reports through official channels. He included no conclusions beyond his remit. Yet the structure of the data suggested a pattern that reliability, timing, and sensory impact formed a connected system rather than separate concerns. Whether higher authorities would recognize this connection was uncertain. The engineer had taken a limited step beyond routine observation, guided by evidence rather than doctrine. The consequences of this step, if any, were yet to unfold. By November 1941, the defensive battle around Moscow entered a critical phase. Temperatures dropped sharply, supply lines tightened, and both sides adapted to winter conditions under strain. Rocket artillery units, now more numerous than in the summer, were integrated into defensive fire plans but still operated with considerable autonomy. Their effectiveness depended less on formal doctrine than on the competence of crews and the reliability of equipment under harsh conditions. At the engineer's facility, his field reports began to circulate beyond immediate technical staff. They did not attract public attention, but they were noted within internal correspondence between artillery departments. Several passages, particularly those addressing ignition timing and salvo cohesion, were marked for follow-up. The focus remained technical, yet the operational implications were apparent to those reading carefully. This attention brought scrutiny as well as interest. A review committee convened to assess whether existing rocket launcher procedures required revision for winter operations. The engineer was invited to provide clarification on his observations. Such invitations were routine but carried implicit risk. Technical discussions could quickly become evaluations of judgment, especially if recommendations appeared to challenge established practice. During the review, questions centered on whether additional inspection steps or procedural checks would slow deployment. Command representatives emphasized urgency and simplicity. Any measure that reduced firing speed or increased preparation time was viewed skeptically. The engineer responded cautiously, framing his answers in terms of preventing misfires and reducing exposure to counter-battery fire. He avoided broader interpretations. Despite this restraint, resistance emerged. Some officers argued that rocket artillery's value lay precisely in its simplicity and expendability. Overemphasis on refinement, they contended, risked undermining mass employment. Others questioned whether the effects described were unique to rocket systems or merely artifacts of limited data. The debate reflected a deeper institutional tension. The Red Army, rebuilding under pressure, prioritized volume and standardization. Individual initiative was tolerated only insofar as it aligned with these priorities. The engineer's work occupied an uncomfortable middle ground. It did not propose redesign, but it implied that subtle factors mattered. As winter intensified, field reports provided further evidence. Units operating with stricter ignition checks experienced fewer launch irregularities, even in extreme cold. Conversely, units that neglected such checks reported increased misfires and staggered salvos. These outcomes were documented in routine after-action reports, not attributed to any single engineer's influence, but the correlation was visible. At the same time, concerns about the rocket system's acoustic signature resurfaced from a different angle. Some commanders requested guidance on minimizing detection after launch, noting that enemy artillery increasingly responded rapidly to rocket salvos. Suggestions included relocating firing positions more aggressively and limiting salvo size. No one proposed altering the sound itself. The engineer observed these discussions from a distance. His role did not permit direct engagement with tactical doctrine, yet he recognized that the same characteristic that disrupted enemy formations also compromised concealment. This duality could not be resolved through engineering alone. It required doctrinal adjustment. Internally, his supervisors advised caution. They acknowledged the value of his observations, but warned against pushing interpretations beyond formal mandates. Wartime institutions tolerated data, not advocacy. The engineer accepted this guidance. He continued to refine his documentation, ensuring clarity and reproducibility, and refrained from speculative commentary. By December, as Soviet counteroffensives began, Rocket artillery was employed more confidently. Its limitations were accepted, its strengths better understood. The engineer's contributions blended into a broader process of adaptation. No directive cited his work explicitly, yet certain procedural changes mirrored his recommendations closely enough to suggest influence. The cost of this influence was subtle but real. The engineer was reassigned away from further field liaison and returned to a purely technical role. Officially, this reflected staffing needs. Unofficially, it reduced the likelihood of further boundary crossing between observation and interpretation. From his laboratory desk, he followed reports of winter operations. Rocket artillery units continued to deliver sudden, concentrated fire, followed by rapid displacement. Their distinctive launch sound remained unchanged, a constant feature of the weapon, whether it was regarded as an advantage, a liability, or simply an accepted characteristic, depended on context. The engineer's role in shaping understanding of that characteristic remained unacknowledged. His work did not challenge authority openly, nor did it seek recognition. It existed within the margins of institutional process, influencing outcomes indirectly through data and procedure. As the immediate crisis around Moscow eased, attention shifted to longer-term planning. Rocket artillery was no longer provisional. It was becoming institutionalized. The question of how its unique features should be understood, technically, tactically, and organizationally, remained unresolved, carried forward into subsequent phases of the war. By early 1942, the immediate danger to Moscow had passed, and the Red Army entered a period of consolidation and reassessment. Losses remained severe, but the front had stabilized. Weapons that had proven workable under the extreme conditions of 1941 were now subject to formal review. Rocket artillery, once marginal, was firmly established as a regular component of Soviet firepower. Within this process, the institutional response to earlier improvisation was gradual and understated. Committees compiled data from multiple fronts, comparing artillery types, rates of fire, reliability, and operational impact. Rocket launchers were evaluated alongside conventional guns, not as curiosities but as systems requiring standardization. Training manuals were revised. Maintenance instructions were expanded. None of these documents referenced individual engineers by name. The engineer returned fully to laboratory work. His responsibilities now involved refining test procedures and assisting in the development of improved quality control methods for rocket production. These tasks were less visible than field liaison, but more consistent with the peacetime structure the wartime state sought to recreate where possible. Some of the procedural changes he had emphasized were now embedded quietly in official practice. Ignition checks were standardized, wiring inspections were formalized, cold weather handling guidelines were expanded. These measures were justified in technical language, citing safety and reliability. The sensory aspects of rocket launches were not discussed explicitly, but the result was greater consistency in salvo behavior. As production increased, so did uniformity. Rockets from different factories behaved more predictably. Launch sequences became more cohesive. Crews trained under revised manuals learned to expect a specific firing rhythm and to displace immediately after launch. These developments reduced casualties and improved coordination, though they did not eliminate inherent limitations. The sound produced by the rockets, the sustained rising noise that had first drawn the engineer's attention, remained unchanged in essence. It was not engineered deliberately. It persisted because it emerged from necessary design features, exhaust configuration, spin stabilization, and launch dynamics. Over time, it became accepted as an identifying characteristic rather than a subject of analysis. German forces exposed to repeated rocket artillery use adapted as well. Countermeasures improved. Units learned to recognize launch signatures and respond more quickly. The initial shock diminished, replaced by caution and procedural response. The weapon's psychological impact, whatever its early significance, settled into a stable role within the broader contest of adaptation and counter-adaptation. From an institutional perspective, this was expected. No weapon retained novelty indefinitely. The Red Army's interest lay in integration, not surprise. Rocket artillery's value was now measured in coordination with infantry and conventional guns, not in isolation. The engineer observed these developments through reports and technical correspondence. His work continued to support incremental improvement rather than conceptual innovation. He did not publish or lecture on his earlier observations. Wartime conditions offered little opportunity for such reflection, and post-war priorities would shift quickly toward reconstruction and secrecy. After the war, rocket artillery entered a new phase of development. Systems evolved, ranges increased, guidance improved. Histories written later emphasized designers, commanders, and institutions. The early period, when engineers worked under uncertainty and pressure, was compressed into summary narratives. The engineer's contribution was absorbed into this collective effort. He neither sought nor received formal recognition. His role exemplified a broader pattern within Soviet wartime engineering: careful observation, cautious adjustment, and adherence to institutional boundaries, even when evidence suggested broader implications. What endured was not his name, but the refinement of a system. The Katyusha rocket launcher became a symbol, often reduced to its sound in popular memory, yet that sound was not the result of a single decision or deliberate design. It was an emergent property shaped by engineering constraints, production realities, and the demands of rapid deployment. The engineer understood this distinction. In his surviving notes, where technical detail outweighed commentary, the emphasis remained on process rather than effect. He recorded what could be measured and demonstrated. He allowed others to decide what it meant. In the post-war years, as documentation was archived and classified, his work receded further into anonymity. Rocket artillery continued to evolve, its early challenges overshadowed by later sophistication. The period when small procedural choices mattered greatly became a footnote in a larger narrative of industrial warfare. Yet within that footnote lay a quiet truth. Large systems are shaped not only by formal design, but by attention to detail under pressure. The sound that came to define the Katyusha was not invented as a weapon in itself. It was noticed, understood in context, and allowed to remain because it did not interfere with primary objectives. The engineer's restraint was as important as his insight. He did not claim effects he could not prove. He did not challenge doctrine directly. He worked within limits, trusting that careful documentation would influence outcomes indirectly. In this way, his legacy aligned with the broader character of unsung wartime labor. It was not dramatic. It did not alter the course of events in isolation. It contributed increment by increment to the functioning of a system under extraordinary strain. The Katyusha rockets continued to scream across battlefields long after his direct involvement ended. Their sound became inseparable from their image. Few remembered the technical choices and procedural refinements that shaped that sound. Fewer still considered the engineers who noticed its implications without naming them. History often records outcomes more readily than processes. In the case of Soviet rocket artillery, the outcome was clear: a weapon that worked well enough, soon enough, under dire circumstances. The process, carried forward by individuals working quietly within constraints, remains less visible. The engineer returned home after the war to a society rebuilding itself. His career continued in technical fields, his wartime experience rarely discussed. Like many of his contemporaries, he carried knowledge that was specific, situational, and largely unrecorded outside official archives. The story of how Katyusha rockets came to sound as they did is not one of invention alone. It is one of observation, restraint, and adaptation. It belongs not to a single moment or decision, but to the cumulative work of individuals who recognized problems as they appeared and addressed them within the limits imposed by time, authority, and war.